Please accept my apologies for not being physically appear in the conference. It is my pleasure to read the presentation about trajectory reconstruction of radiosondes for checking fluctuations inside one cloud. My presentation includes 5 parts. First, I will introduce the objective of the project and my work. Second, I will talk about the methodology which is being applied in the work. Next, some recent results, and then the future plan will be presented. And finally, there will be some discussion about the problems that we are facing. Regarding to the objective of my work, we are working on developing a new kind of balloon radio source for collecting information from one cloud, such as pressures, humidity, temperature, and air fluctuations. As a result, I have to develop an algorithm to reconstruct the trajectories of the radio source inside the cloud from inertia data. For example, accelerations and rotation rate of the radio source. See a prototype of the balloon radio source. The cover is a new material which is being developed by another engineer. And my electronic circuit is supposed to be inside the balloon. There are some general requirements for the balloon radiosondes. First, they shall be low cost, since they are supposed to be used just once and be disposable. Second, the total weight of each balloon shall be around 20 to 30 grams. Furthermore, their working time shall be up to 5 hours. From the weight and working time constraint, the electronic circuit shall be low power consumption. Now we move to the methodology. We knew that in theory, the move displacement is double iteration of the accelerations, and the rotation angle is the iteration of rotation rate. The position in the balloon's body frame calculated from the accelerations will have to be transformed into the earth frame via a rotation matrix, and so in the last equation in this slide. Generally, inertial navigation and positioning systems usually use accelerometers to measure the linear accelerations and use gyroscopes to sense the angular rates. However, it is feasible using only accelerometer to determine all the angular velocity and linear accelerations of an object. And so in this figure, with the two accelerometers repeatedly mounted into the body, the angular rate can be calculated by these two equations, and so the electronic circuit is supposed to include 4 accelerometers, with one of them is placed at the center of the gravity of the balloon. The 3 others are placed in the 3 axes respectively. So the angular rate can be calculated from the differences of the output of the accelerometers as shown in the 3 equations here. The question here is that why do we use accelerometers instead of inertial measurement units? The answer is the power consumption. One accelerometer needs a current from 150 to 350 microampere, while an annual requires 2 to 4 milliampere. The graph describes the flow chart of position calculations or trajectory reconstruction of the objects from the inertial data. First, the raw data from the accelerometers was resampled and filtered to reduce the impacted noise. After that, the integral was upgraded to calculate the radiosonde's position in its body frame and its orientation. Then the rotation matrices we calculate from rotation angles were upgraded to transform the position from radiosonde's body frame into the Earth frame. Now we move to the third part of my presentation. This is the first prototype of my electronic circuits. You can see from the picture here the accelerometers, the Arduino Pro Mini, and the pressure, humidity, and temperature combinational sensor. This prototype includes only two accelerometers, so up to now I can only reconstruct the movements with no rotation and test the rotation around these axis only. The results of non-rotating movement reconstructions were shown in the two pictures here. For the 2D test, the balloon radiosondes was set to move through two perpendicular straight lines with form 45 degree angles with x and y axis. X lies a diagonal of a square with peak at equal 0.6 meter. The errors in the peak directions was around 10 centimeter and in the y directions was slightly higher than 5 centimeter. For the 3D test, the proposed movements of the balloon radiosondes were similar with the 2D case in x and y direction. In this direction, it was set to fluctuate before coming back to zero. Uh, in this case, there were nearly no difference between the proposed movement and the reconstructed trajectory. These two pictures describe the results of calculation of the balloon orientation from the accelerometers data. In the first case, the balloons were set to rotate around 90 degrees directly, and in the second case, the balloons were set to rotate the same angle, but by two steps. The results here prove that is able to determine the rotation rate and rotation angles from accelerometers data. In the future, the range of accelerations and rotation rates will be defined for choosing the right accelerometer. After that, the full circuit with 4 accelerometers will be implemented and tested in 3D environment. Next, the circuits will be integrated with the transmission part, which, which is being developed by another engineer. Then the balloons will be tested uh, in the later environment. And finally, the power consumption and the total weight will be optimized. The problem that we are facing now is that in general, positioning and navigation application requires at least two sources of information. For example, GPS and inertial data. However, because of weight constraints and transmission bandwidth limitations, we are now using only inertial data from accelerometers. For replacing GPS, we are thinking about using received signals change indicator measures uh, based on ground stations. However, this will lead to increasing the number of ground stations to at least 4 instead of just one. And that is the end of my presentation. Thank you for the